Hello students, we're going to talk about buffers and acid-base titration curves. This section's a little bit more challenging and it's probably going to be fairly new for most of you if you came from Chem 100, 130. So we'll also be discussing it in the Zoom discussion section. Okay, so buffers are very important for us to understand in biochemistry. And a buffer contains a weak acid and its conjugate base. So I'm going to write that in here. So an acid-base conjugate pair. So you could have a weak acid and its conjugate base. Or you could have a weak base and its conjugate acid. So in the next slide, we'll practice kind of that relationship again. And the important part about buffers is that these are solutions that help resist changes in pH upon addition of a strong acid or base. So I'm going to add that in here. So upon addition of a strong amount of a small amount of H plus or a small amount of hydroxide. And so why is this important? As we'll see later, that our bloodstream's buffered. And so we have to keep our bloodstream's pH around 7.4. And so that's why the bloodstream has a weak acid and its conjugate base present. But more on that a little bit later. Okay, this picture is just, or the rest of the slide is just like an overview. So a weak acid's most effective buffering range will be plus or minus 1 unit of its pKa. We'll come back to that. And then titration curves are used to determine pKa values, and we'll also come back to that slide. Okay, so let's practice then. Let's say that I have a solution of acetic acid. By itself, it's a weak acid. But if we have it in a flask in a solution with its conjugate base, acetate, remember a conjugate base is 1 less H plus. So when we have it, a solution with both weak acid and conjugate base, that's going to be a buffered solution. Okay, and the equation that describes this reaction is the ionization equation for the weak acid. So remember, acids lose H plus to form hydronium ion. And in this case, conjugate base, acetate. This is a weak acid. So we're going to show the double arrows. Remember, those will have an equilibrium. And then we'll write this out as Ka equals hydronium times acetate over weak acid. So that's our Ka expression. And at 25 degrees, Ka equals 1.8 times 10 to the negative 5. Where did I get that number from? This would be given, you know, it's a standard value from the back of most textbooks. Okay, so let's talk about a buffered solution. Let's picture that in this solution, I have 1 molar acetic acid and 1 molar acetate. Okay, what is going to happen in terms of the Ka expression? Okay, so I'll come up here and write it. I'm going to say 1.8 times 10 to the negative 5 equals H3O plus 1 molar acetate over 1 molar acetic acid. So that's because I substituted, right, the concentrations of those into the expression. Now, what you should be noticing is that when the concentration of conjugate base is equal to the acid concentration, the weak acid concentration, we have a very easy relationship here. Ka equals H3O plus. And then let's think about what pH would equal. pH equals the negative log of this number, which you could take a minute to plug into your calculators. You could pause me. But we'd get a pH of 4.74. So we know the pH of this solution. Now, here's what's interesting, is that pH equals negative log of the H3O plus, but this also equals Ka, right? That's the Ka value that was given. So actually, I can also say that the pKa is 4.74. So really what we're seeing is that this is the easiest buffer where the acid, I'm going to call the weak acid HA as a generic term, and the conjugate base A minus as a generic term. HA equals A minus in this buffer. So pH of the buffer equals pKa. This is always true for any weak acid conjugate base system. Okay, so in a buffer, though, you won't always have equal amounts of those, right? So how will it change if we add more weak acid or more conjugate base? And so let's take a look at that part. I'm going to erase this. Okay, so you can rewind if you need more of this. So we'll come back to that. You can go back to that, I should say. Okay, so I'm getting fancy with my eraser here. All right, so let's say we now have a different scenario where instead of being 1 molar of each, let's say that I have 1.5 molar of acetic acid and 1 molar of acetate. So I have more of the weak acid than I do base. Now I can plug those numbers into the Ka expression down here, but I want to show you something that will be very, very helpful to you, and that is that we can convert this expression into one of the most famous expressions in chemistry called the Henderson-Hasselbalch. Now, I don't want to show you the derivation because it gets overwhelming, but basically it takes this expression down here and you take the negative log of both sides and you do some algebra. And once you do all of that, you would end up with the following expression. Now, I really love Henderson-Hasselbalch, but I'm kind of nerdy. But the reason why I love it is that it's just so much easier to understand buffers from there. I didn't like the way I wrote that. So why do I think it's so much easier? Let's take a look. What this equation is showing us is that in a buffer, the pH is going to hover somewhere around pKa. What is going to affect where the pH lands is the ratio of A minus over HA. This ratio determines where the pKa ends up. So this ratio is important. Now, going back to the previous example, A minus equaled HA. They were both 1 molar. So if they're both 1 molar, pH equals pKa because A minus over HA equals 1. The ratio is 1, and the log of 1 is 0. So this is where we ended up with pH equals pKa. Okay, now let's take a look at this example. My ratio is not 1 because one of them's 1.5 and the other one is 1.0. So let's plug in pH equals pKa. Now the pKa, our Ka is 1.8 times 10 to the negative 5. So the pKa is 4.74. So if you need me to, I'll show you again where that number would come from. That's the negative log of Ka. So pH equals 4.74 plus the log of A minus, so here's our new one, 1.0 over 1.5. Okay, notice our ratio is less than 1. Let's plug in to the calculator. Take 1 divided by 1.5, that's 0.67. Now I'm going to take the log of that number. We get a negative number, and then I'm going to take that number, and I should end up with 4.56. Now, conceptually, the concept here is that we have more acid than base. So the pH should be lower than pKa, more acidic. So we have more weak acid. So the pH that we get is lower than pKa. Okay, so this ratio is so important, because this ratio, oh, that didn't work, did it? The ratio is so important because it tells us where we're at relative to pKa. Okay, let's try one more scenario. Okay, so let's say that I have acetic acid. So that one is going to be 1.0, and let's put the other one at 1.5, the conjugate base. Okay, now let's plug in. pH equals 4.74 plus the log of 1.5 over 1.0. Okay, so go ahead and find your ratio. Take 1.5 divided by 1, which would be 1.5, right? So right away, we know that A minus over HA is greater than 1. It's more basic. So now I'm going to take the log of 1.5, and we're going to get a positive number, and we're going to add it to the 4.74. So I get 4.92. Which makes sense because we have more base, right? More conjugate base than weak acid. So what is very important are these ratios. Like they decide, the ratio decides what the pH is. So if the ratio base to weak acid is less than 1, you have more weak acid, the pH is lower than pKa. If your ratio is greater than 1, then your pH is greater than pKa. Okay, so what does this all tell us then? I think it tells us two really important things. When we're making buffers in a lab, the ratio of A minus to HA determines really the pH. But the other important thing is the pKa is critical as well. So buffers only can guard a certain pH that is around their pKa. And so I'll highlight that here, and I think it's in the next slide as well, but I'll put it here. This particular buffer system of acetic acid and acetate ion, the pKa is 4.74. We'd have to be given Ka to find it. That's kind of a given value. That means that this is only a good buffer system. It has to hover around that particular pKa. So the pH range that this is going to work for is actually a range of 3.74 to 5.74. Like that's the pH range that this solution will work best in resisting changes to pH. So if somebody says to you, hey, we want to make a buffer, the first thing you'd say is, well, what pH range do you want? Because that's going to determine what buffer system you use. And then the second thing would be to figure out what ratio you need. Okay, let's go to the next slide. This slide has a lot of math, but I think it just is there to help you to understand what buffering capacity means. Like this is the ability to resist H plus and OH minus that's added. Okay, so here's acetic acid. This shows it as 4.76. Most textbooks would show it as 4.74. So I'm so used to the 4.74. If you don't mind, I'd like to use that. Might be a little confusing here, but I already used it, so I'll make that correction here. Okay, so if we have 1 molar of each, okay, anytime HA equals A minus, pH equals pKa, always, because the buffer ratio is 1. So this particular, and I'm going to change this to 4.74. So if we have 1 molar of each in this solution, okay, then the pH equals 4.74. Okay, now what happens to our buffer system when the H plus increases? And there can be all sorts of reasons why that happens. So here I have HA and A minus floating around in there. Starts off 1 molar each, okay? But now let's picture that we add H plus to this. So I'm going to use a different colored pen for that. Let's do green. Okay, so H plus is added. Now, normally, strong acid is going to make the pH plummet. And that could be a really bad thing. In the body, that's not a good thing. We can't tolerate huge changes in the pH of our blood. So that could have devastating consequences, which we'll talk about a little later. But here's what's going to happen here is that in a buffered situation, one of the two species will react with H+. So the question is, from all your chemistry, we have weak acid, we have acid, HA, and we have base, A minus. So the question is, will H plus react with another acid, or will it react with a base? So hopefully you said that it reacts with the base. So A minus is going to neutralize the H plus. Okay, let me show you this with some math. It just is there to help you. Initially, we started off with 1 molar of each of these. And if it's 1 liter and it's 1 molar, then this would be 1 mole of each. Now let's picture that we add 0.1 moles of H plus. So some of the A minus is going to neutralize it. It's going to go down in the amount. You're going to make more HA. Okay, and why is it 0.1 and 0.1? Because the mole ratio is 1 to 1. So remember some stoichiometry. Okay, now what does this mean is that now our buffer goes up in terms of the amount of HA and goes down in terms of the amount of A minus. We can plug this into Henderson-Hasselbalch. Right? We plug the 0.9 in for A minus, the 1.1 for HA. And notice what happens is the pH of the buffer changes. It went from 4.7, I'm going to say 4.74. And then let me calculate it with that correction there. .65 is what I got with the correction of that pKa. So it does go down. The pH does go down because you added H plus. It just doesn't go down by a lot. So what we're seeing here is that the buffer resists changes in pH. Some highlights of this. are that when H plus is added, it's always going to react with A minus in the buffer. Always, because an acid reacts with the base. Okay, not shown here would be another scenario where if you added hydroxide to this. So I'll look at that on the next slide. Okay, I'll show you that scenario. Okay. Okay, so let me show you the scenario here. Let's say I have a weak acid and its conjugate base, and we decide, or something happens in the solution where the solution becomes more basic with hydroxide. Okay, so the question is, does an acid react with a base, or does a base react with a base? So the answer is that the acid in here should react with that base. So HA plus hydroxide will make A minus and water. So this is always true, that if we have hydroxide added to a buffered solution, the weak acid in it will react with it. Okay, now what will that do is it's going to change the pH of the buffer. It's going to make it a little bit more basic than it was before. And let's see if we can see why. So if here's the Henderson-Hasselbalch equation. In this scenario, A minus is going to increase because you're making it over on this side, and HA is going down because it's getting neutralized. That means the pH is going to be increasing. But it's going to be slight. Okay, now one other thing that I think is important to mention is that good buffers okay, first of all, of course, the pH is always going to be plus or minus. It's going to hover around that pKa. The second important thing, though, is if you want a good buffer, you want it to be able to neutralize a whole bunch of weak acid and conjugate. You want it to be able to neutralize a whole bunch of added H plus or hydroxide, which means that you really want high concentrations of HA and A minus. So to give you an impression of what I mean, like, you might want 2 molar HA and 2 molar A minus. That's a better buffer than if these were really dilute. Both of these buffers, pH equals pKa because they're equal in concentration, HA to A minus. But this first buffer is so much better. It has a greater buffering capacity. It can neutralize more acid. I'm going to put that as capacity, sorry. And what do I mean by that is you can add more OH and more H plus can be added and still keep the buffer functional. You can add more with higher concentrations and it can still neutralize it. Okay. All right, so Henderson-Hasselbalch, the pKa of the weak acid is so important, and it's really going to decide which buffer system we used. And the pKa is, of course, a measure of acid strength. And then the pH is determined by the ratio of A- to HA. Okay. This I already went through, so this is prettier. I already went through this, that if the pH is less than the pKa, you have more HA. So this ratio is less than 1. When the pH is greater than pKa, you have more conjugate base. And it's greater than 1. Okay. Here's some weak acids, and I want to highlight some things, but I believe I put it on the next slide with a little bit more room. So these are some common biochemistry acids with their pKa's and Ka's listed. So I put it here, and here's what I want you to think about, that if we are selecting a buffer, so if we want to select a buffer system for our physiological pH, of 7.4, we can look these guys over and see which buffer system is going to work. Remember, its pKa has to be plus or minus 1 unit from the pH that we want. So in other words, we have to get it close to 7.4. And so let's take a look. Take a second. There's one buffer system that's the best out of these. If you notice, here we have the 6.86. So in other words, for the pKa, hold up. So for the pKa, that's equal to 6.86, that's going to be able to resist changes within 5.86 and 7.86, and that is going to be good for our 7.4 that we want. Okay, so out of all the buffers listed, our best one for physiological pH is H2PO4 as the weak acid and HPO4 2- as its conjugate base. And you're going to do a whole worksheet. We're going to talk about it. With this buffer system, it's in the kidneys. Okay. Now, there's one more here that's kind of close, and that is the carbonic acid one. That one is right there. Oops, I don't like the red, sorry. At 6.3. So it's close, and interestingly enough, this is a very important biological buffer, carbonic acid with bicarbonate. Now make sure that you understand why they're conjugates of each other. H2CO3, 1 less H plus will give us the bicarbonate. Okay, between these other two, H2PO4 minus, 1 less H plus gives us the HPO4 2 minus. Okay, now its pKa is 6.3, which means that it's going to resist changes in pH between 5.3 and 7.3. So if you notice, it's cutting it pretty tight to our physiological pH. And we will talk about this. This is our predominant buffer in the bloodstream. But we're going to see that it's almost out of buffer range, but we'll still talk about why it still works. Okay, so out of all of the buffers listed here, out of all of the weak acid conjugate base systems listed here, these two would be the only one that would be appropriate for 7.4 physiological pH. Okay, because it's close to the pKa values for that buffer system. The other important point is that, especially if you look here with HPO4 minus and HPO4 2 minus, I'm sorry, I might have said that wrong, H2PO4 minus and HPO4 2 minus, okay, those guys are a buffer system. The phosphoric acid you see up here with H2PO4, that's a completely different buffer system. We don't mix and match them. Okay, so phosphoric acid, H3PO4 here, it actually has 3 ionizations, first, second, third, which I wrote out in a previous PowerPoint video lecture. 3 ionizations, each is its own separate buffer system. Okay, and the only one out of these 3 that has a pKa close to physiological pH is dihydrogen phosphate ion and monohydrogen phosphate ion. Okay.